Hey ho, by the time you get to grade 11 and 12, the chances of you not having seen a Venn diagram is pretty small, but I'll go through them very quickly just to make sure that you're good to go. So I'm going to start off with an example, and just a reminder that a Venn diagram is a way of representing your sample space and is usually good for two or three separate events that you want to sort of be able to combine in some way. So the example I've got here is, again, the old faithful dice roll. So two dice are rolled and their faces are added together. And I've specified two events. A is the event that an even total is rolled, and B is the event that a factor of 12 is rolled on the total dice. So I'm going to start by constructing my Venn diagram. All Venn diagrams should be contained within a box like so. And then we use circles to represent the sets of outcomes for an event. So that's where it's basically the same, but there are different ways you can represent the numbers, I suppose, in the sample space. So here we go. I'm going to look at event A, and I'm going to construct it in a bit of a weird way. Just for those of you who know Venn diagrams, what I'm doing is a little bit weird, but there's method in my madness, and hopefully it'll make sense as I go along. So let's look at event A. A is the event that an even total is rolled. So I roll two dice. I'm going to get a 2, a 4, a 6, an 8, a 10, or a 12. Okay, that's the even ones. Event B is that a factor of 12 is rolled. So that'll be 1 goes into 12, 2 goes into 12, 3 goes into 12, 4 goes into 12, 6 goes into 12, and 12 goes into 12. So these are all of the numbers that go into 12. And then that leaves me with 1, 2, 3, 4, 5, 7, 9, and 11 are the numbers that don't fit event A or event B. So that's a Venn diagram. I should label this A and label this B so it makes sense. And it's pretty common to do something like this. That little epsilon symbol there means the sample space, and the n bracket means the number of items in that sample space. So the number of items is equal to 12. Everything from I can't roll a 1, can I? That's not in the sample space at all. There we go, get rid of that. So I can roll everything from a 2 to a 12. So that's going to be a sample space of 11, I think. Okay, now it's a bit weird because what I have here is I have some numbers that are appearing in event A that also appear in event B. So in a Venn diagram, those that are common to both go in the middle. So there's 2, get rid of them as I go along, 4, what else we got? 6, 12. There we go. So really, in a Venn diagram, each item should be represented just once in one part of it. So this bit is exclusively A. This would be even numbers that are not factors of 12. This is exclusively B, which would mean factors of 12 that aren't even. This is both of them. So it's effectively A intersect B. And funnily enough, the circles are intersecting. So it kind of makes sense with our language as well. And then 5, 7, 9, and 11 are 4 numbers that are neither even nor are they factors of 12. And if I count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there's my 11 outcomes. It matches that. Now, what I've drawn there is one way of writing a Venn diagram where you've got the outcomes literally listed. But you might remember that I said in a couple of videos ago that quite often we don't need to know the actual outcomes and we're just interested in the counts. And it's much more common to put the counts in the diagrams rather than the actual specific outcomes. So in other words, instead of putting 8 and 10 there, I know that there are 2 matching outcomes, so I put 2 there. In the middle, instead of putting 2, 4, 6, 12, I just put 4 there. There are 4 matching outcomes. Instead of putting 3, I put 1 matching outcome. And instead of 5, 7, 9, 11, that which doesn't meet A or B, I put 4 as well. So again, that's not the numbers that you're rolling on the dice, but the number of outcomes that match A, match B, or match neither. So from this, if I add the numbers up, 2 plus 4 is 6, plus 1 is 7, and 7 plus 4 is 11, which gives me this number here. That's how it should work. And then I'm good to go. So in terms of representing what's going on here, I'd be saying things like the probability of A is equal to 2 plus 4, 6 over 11. Okay, so the probability of A is this bit here, but this is also part of the circle of A, so I'd add them together to get 6 over 11. If I had the probability of A and B, that would be 2 plus 4 is 6 plus 1 is 7 over 11, etc. That's how I would do it. So that's a really common way of representing it in a Venn diagram. Not quite as common, but it certainly is done, is this representation. So I'm going to go and draw another Venn diagram. Same example. 2 circles. Oh gosh, see if I can do a circle instead of an ellipsis. Ellipsis. That's not what I meant. Okay, so there's A and B. It's not that uncommon to write down the probabilities instead, often as decimals, but I'll just do them as fractions because it's actually just easier for my little brain. So here I would have 2 elevenths, here I would have 4 elevenths, here I'd have 1 11th, and here I would have 4 11ths, with this really, I suppose, would be probabilities. So you put the probabilities there instead. Usually when it's a decimal, which I just didn't bother working out because 2 11, they're all just non-terminating decimals, and I didn't want to try and figure them out on the fly. But in another example, it might be 0.2 here, 0.4 here, 0.7 here, and whatever that would end up being. I reckon the numbers I just gave you were rubbish then, but you get the idea. Yeah. So what you can do is you can then answer questions like, what's the probability of A, and then from that diagram you'd be going 2 11ths plus the 4 11ths in the middle, which is equal to the 6 11ths, which is the same as I've got above there, of course. But you can do it from a representation of probabilities as well. Okay, let's just have a look at the probability of A intersect B, and let's use slide 15 as our example here. We have the probability of A intersect B. How would we work that out? Well, we'd work it out by saying 2 11ths plus 4 11ths plus 1 11th. Yeah. So that would be equal to, oh, sorry, that's completely wrong. Beg your pardon. I made a mistake up above as well. I won't redo the video because I'm happy for you to see my mistakes. The probability of A intersect B is, of course, just the middle. And so that would be just 4 11ths, like so. Okay, so that is what should be there as well. It's just the middle itself. But what about the probability of A union B? Well, that would be 2 11ths plus the 4 11ths plus the 1 11th, which would be equal to 7 over 11. And what about the probability of B? Well, the probability of B would be equal to 4 11ths plus 1 11th, which would be 5 11ths. Now, the reason why I wrote all those out is because I wanted to make a point about some really simple probability arithmetic, and it's the addition law, I suppose, of probability. So if you have a look at this, the probability of A union B, at a very simple level, you'd think would be the probability of A plus the probability of B. After all, that's what we did in the weighted trees, right? But if we did do that, let's have a look. Probability of A plus the probability of B, that's the probability of A there, which is 6/11ths, which is what we worked out. That's the probability of B, which is 5/11ths, as we've worked it out here. If I added these together, can you see that I would be adding this intersection in twice? And because I'm adding this intersection in twice, I would be over-representing the probability. So in order to remove that double up, I'm going to have to subtract the probability of this intersection. And so that leads me to the addition law for probability, which is that the probability of A union B must be equal to the probability of A plus the probability of B, but then we have to subtract the probability of A intersect B. Okay, so from a Venn diagram, I hope that makes sense. Here's an example where you might be just given a probability calculation to do. You might be told the probability of A is equal to 0.5. I'm making this up as I go along, so it's wish me luck. The probability of B is 0.7, and the probability of A, watch this, union B is equal to 0.8. And the question might be, what's the probability of A intersect B? Okay, so what you would do is you would just state the law. Well, I'm doing this for completeness sake. You might just want to go straight to the next step. A union B is probability of A, probability of B, minus probability of A intersect B. Substitute what you know. 0.8 is what we're told is the probability of A union B. 0.5 is probability of A. Probability of B is 0.7. A intersect B, like so. So we've got 0.8 is equal to 1.2 minus the probability of A intersect B. Now I'll subtract 0.8 from both sides. 1.2 from both sides, and I get negative 0.4 is equal to negative the probability of A intersect B, i.e. the probability of A intersect B is equal to 0.4. Now pause the video and quickly draw a Venn diagram for it. Have you done it? We'll do it. Pause it. Do it. Okay, assume you have done that. So quickly, Venn diagram. I've got A here, got B here. I've got the probability of the universal set is equal to 1. And I guess I'm going to have to assume that, not necessarily, let's see how we go. Okay, so the probability of A intersect B is 0.4, so I'll fill that in here. The probability of A is 0.5. Now, if the probability of A is 0.5, but the intersect is 0.4, that means that must be 0.1. So the combined total of those two must be 0.5. Now, if the probability of B is 0.7, but the middle is 0.4, this must be 0.3. It's the probability of just B, nothing else. Now, if I add these up, I get 0.4, 0.3, which is 0.7, plus 0.1, which is 0.8, which is what you'd expect. So therefore, the probability of neither is 0.2. So the probability of neither, by the way, is like this. It's A union B, that's all the circles, complement, which often just gets written as probability of A union B complement like that. And that's 0.2. So just as a bit of an aside. Now, one more little example. I'm just going to have to add a slide for that so there's no little lines to separate it out, but I'm sure we'll survive. Is have a look at this. Probability of A is equal to 0.3. Probability of B is equal to 0.5. And the probability of A union B is equal to 0.8. What's the probability of A intersect B? See if you can do that problem by pausing the video. Okay, you've either done it or you haven't. Now, you might have even been able to do this problem without even doing a calculation if you'd sort of kept your head and had a look at it. But I'll do the calculation so you can sort of see. This time I'll go straight into the calculation though. So A union B is 0.8. Probability of A is 0.3. Probability of B is 0.5. And I've got minus the probability of A intersect B. So I've got 0.8 is equal to 0.8 minus the probability of A intersect B. And then that will give me 0 equals minus the probability of A intersect B, i.e. the probability of A intersect B is equal to 0. Perfectly legitimate. Perfectly legitimate. Again, pause the video. Draw a Venn diagram. Did you do it? Hope so. Here we go. So this is what it would look like. I'm going to do my circles. Okay, so this is A, this is B. And we've got, I didn't leave myself enough room here, so I'll just put it up here. So the probability in here is 0, which means that the probability on the left-hand side must be just straight old 0.3. This must be 0.5 out here, and this must be 0.2 here. Okay, but this is a bit weird, isn't it? That's a bit weird. You've got an intersection, but there's nothing in it, which means they're not actually intersecting. So genuinely, it should be drawn like this. Drawing it a little bit smaller because I want to put some notes underneath. Oops. Okay, so we've got A. Oh man, I'm just so used to doing it. I didn't do what I was meant to. This would be A, like so, and this would be B. Should be the same size circles, but doesn't matter. So this is A, this is B, and there's a definite gap between them. 0.3, 0.5, and neither A nor B, 0.2, like so. So we've got two circles that are not intersecting. The probability of A intersect B is 0. The number of items in A intersect B is 0, so they're completely separate circles. When you have two events where the probability of A intersect B is 0, we call them mutually exclusive events, and I'll put that underneath. Mutually exclusive events. It means there's no possibility that both events can occur at the same time. So, for example, you get to an intersection on a road, you can either turn left or you can turn right. You cannot do both. And so the event of turning left or the outcome of turning left and the event of turning right or the outcome of turning right are mutually exclusive. There's no chance you can do both. Okay, so that's what mutual exclusive means. And if you ever need to represent mutual exclusivity, then a Venn diagram with two separate circles would be the exact way to go. Okay, I'm going to leave it there for this video because it's gone on long enough and it's mostly an explanation video on how to do a Venn diagram. It's your chance now to do as many examples as you can, working out probabilities from it. We'll revisit Venn diagrams when we get to conditional probability as well. But critically for you, you need to know that you can have 2-circle, 3-circle Venn diagrams, never more than 3 circles though. So do as many examples as you can in order to practice putting these together and reading those Venn diagrams to answer probability questions. Okay, I'll leave it there.